Okay, so I hope you're able to see the PowerPoint. So as we have discussed, so first in the first lecture, we talked about just in general the quantum theory we sort of developed based on the experiments, and then later on we have developed this linear algebra notation, the Dirac notation. So the take-home message from the last lecture from Dr. Gargi was that these quantum states, the information encoded in the preparation, can be represented as vectors in a vector space, right? And then linear transformations via matrices describe how quantum states evolve over time, right? So these simplify what would otherwise be complicated quantum calculations, right? And so we would say that a quantum state system is a vector and its evolution is a matrix multiplication. So the Hamiltonian is a matrix, an operator, and then we can use that to evolve the system. Very quick introduction: a vector is an ordered list in the secondary sense. In the primary sense, a vector is something that has magnitude, that has length and direction. But in a secondary sense, once we project it onto a basis, then we can write it as a column matrix. So when we write it as a column matrix, what that implicitly means is that there is a basis that is associated with it. So when I say, for example, I have, let's say, in Cartesian coordinates, if I have a vector that is, let's say, 2i plus 3j plus 4k, something like that, and I write this vector A as a column matrix 2, 3, 4, then I'm implicitly denoting that this 2, 3, 4 are the components that are with I, j, and k, right? And so usually one of the mistakes that people make is that when you're looking at these numbers, they think about these numbers as scalars. But these numbers are not scalars. These vector components are not scalars. So a scalar is something that does not change when you change the coordinate system, when you change the basis, when you change basis. When you change the basis, right? But if I change the basis here, instead of ijk, if I considered some other basis, right, that's rotated by, let's say, a few degrees, then obviously these components would change. So these numbers, while they look like numbers, they're not to be confused with scalars. So in general, for a given basis, we can represent a matrix, a vector as a column matrix. But when we represent it as C1 to Cn, that means there is a basis associated with it, right? And these are the coefficients that are related to that basis. So keep that in mind. And then, simple additions, the components add. So because these are related to the basis vectors, only that particular basis vector components add. So C1 and C1 prime belong to the same basis vector. So they add up, right? Straightforward there. And then if you multiply with lambda, this lambda we would say is a scalar, because this won't change with, this is not related to the basis. It's a single element. You see, although it's a number, right? It's still a single element, won't change if you change the coordinate system. So when you multiply with the scalar, you multiply each and every component with that scalar. And so I have some simple examples here which you can check out. And then you have the three properties of vector operations: commutativity, associativity, distributivity, right? I'm pretty sure that all of you know this, so I'm not going to spend too much time on these things. So we discussed about the inner product. So when we are doing the inner product, what we do is a dot product. So when we do a dot product, what we mean to do is we are measuring what is common between two vectors, right? And so that's the basic definition of dot product. So when I look at the dot product of V and W, that each of these components is related to a basis vector. So I see what is common between those basis vectors. So in general, in quantum, these entries in the column vector could be complex. So we will see in Numpy very soon that there is a different way to take complex conjugate and do the inner product for real vectors versus complex vectors. But essentially, when you do this, you have to take transpose because the vector multiplication, right? So you would get Otherwise, the order wouldn't match. So when I take the transpose, then I would get n by 1, sorry, 1 by n times n by 1. So I would get 1 by 1 as the result when I multiply. So I get a number, right? So, and again, this, what I get here after the inner product, that would be a scalar. So if I look at the inner product VW, right, or it could also be written as VW, right, different types. This wouldn't change even if you change the basis, right? This would remain the same even if you change the basis, because all the components of V and W would change accordingly, right? So the magnitude would be the square root of the inner product, right? That's something, again, very, very simple. And I have a couple of examples here. And then we briefly discussed orthogonal and orthonormal basis, where you have these basis vectors. If I is not equal to j, then they're 0. If I is equal to j, then they're 1, right? Just like ijk in case of Cartesian basis. And then you have m by n matrix with m rows and n columns. When you do a transpose, you change the rows into columns. And if you have um, conjugate, adjoint, or like when we talked about Hermitian conjugate, so we would take complex conjugate of each element and then transpose it, right? And very simple matrix multiplication and linear transformations here, just for the sake of completeness. And I'm not going to go through it because again, like, I'm pretty sure that you guys are familiar with this. We briefly touched upon a unitary matrix. Unitary matrices are very, very important for us because when the Hamiltonian is time independent, we could use the unitary matrix to look at how the quantum state evolves, right? So a unitary matrix is defined as where this U dagger or U bar, where it is the complex conjugate transpose, is equal to U inverse, or U dagger U is 1, right? So the unitarity preserves the inner products, right? That is, the probability, for example, is preserved. The total probability remains 1, right? It does not change. So what we are going to do in this lecture is we are going to look at some of the basic Numpy and Qiskit. And I have these links here. The first link is for Numpy and the second link is for Qiskit. We will get started with initiating qubits and making some measurements and show like how we have discussed in case of state preparation in the last 2 days. We will see some of those results using Qiskit. So I am going to open that, and Dr. Gagi is going to send this PowerPoint to you, so you can look at these. So let's go to the Google Colab, right? And so let me zoom in. Okay, that's too much, I think. Okay, so I hope all of you are able to see that. And so for those of you who know NumPy, this should be pretty straightforward. So here, to begin with, first what I want to do is I want to define, we have seen the state vectors. For example, in Dirac notation, I can write a state 0, right? As, let's say, we have a one-dimensional well, right? And let's say the potential is infinite here. And then I have psi1 of x, right? And then psi2 of x, so on and so forth, right? So I could take the psi1, psi2 as the basis. I could take the psi1, psi2 as the basis, and I could write, for example, 0 as a combination of these two, right? So I could write this 0 state as just simply let us say psi1, right, is related to psi1 of x, and 1 is psi2 of x, let's say. These could be anything. right? So these are the basis vectors. So I could express this 0 vector as, let's say, a column matrix 1, 0. That means when I go to the basis, right, this would be 1 times psi1 of x plus 0 times psi2 of x. So this 0 is simply saying like psi1 of x, right? And so state 1 would be, you could represent this as 0 and 1. So this 1, 0 and 0, 1, they are not, they themselves are meaningless without the basis, right? These are just components. And so you need to think about what is the basis that we are referring to, right? So here it could be these states in the 1D well, it could be harmonic oscillator, it could be spin, whatever it is, right? So the first step, what we will do is, we just basically use Numpy to make these states, right? So we import Numpy as NP so that we don't have to write Numpy every time. So we can just write it as NP. So whenever you want to use something from Numpy, you use NP dot that function. So I'm creating the state 0 here with NP dot array 1, 0, right? So that means it is going to create a column vector that looks like this. And then state 1 that I'm going to create like this, np.1. And then I'm going to print that, right? So let's run it. It's connecting. Okay, so it connected, and then we get this 1, 0 and 0, 1, right? So that's pretty straightforward, right? So now the first example is, now we want to create a NumPy array to represent a quantum state that is a superposition of 0 and 1. And here we are just putting 1 over square root 2 so that the total probability is 1, right? So then the superposition would simply be 1 over square root 2 state 0 plus state 1, right? So then I can run that, and then you see that the superposition state is giving us same value for 1 over square root 2 is same as 0.707, right? So that state 0 and state 1 are being put in superposition state. Then we talked about inner product, right? So ask yourself, right? We have these vectors 0 and 1, which are related to psi1 and psi2, for example, the way we defined them. So what do we get if we take the inner product of 0 and 1? What would be the inner product of 0 and 1? You can reply in the chat. What would be the inner product of 0 and 1? Okay. So I see that most of you are able to see that the inner product of 0 and 1 is 0 here. Again, this depends upon what 0 and 1 is, the way you have defined, right? They're orthogonal, that's right. So you can just do, in general, when we want to evaluate inner product, you can just do a dot product. But here you see I'm using this command called v dot. V dot is different from np dot. So in this case, both numbers are real numbers. 1 over square root 2 is a real number. So it doesn't matter whether you use dot or v dot. But if you have, in general, a complex number, because these coefficients can be complex, right? You want to take the complex conjugate also, not just a transpose, but you have to take the complex conjugate also. So if you do v dot, it accounts for the complex conjugate as well, rather than np dot, right? So this evaluates the dot product, right? So as you see, the inner product of this is 0, right? For example, if I change this to state 1, right? What would I get? That's right. So we should get 1, right? So because the inner product of 0 and 1 is 1, right? So again, the main point here is, for those of you who are not familiar with NumPy, v dot is more general, that handles even the complex conjugate, right? So then the exercise is calculate the probability of measuring 0 if the system is in the superposition state we created in example 1, right? So then we then do state 0 and then the superposition state. So we are taking the inner product of state 0, right? So the superposition state is 1 over square root 2, 0 plus 1. I don't think you can see what I'm writing. So 0 plus 1, that's a superposition state. And what we want to do is we want to find the probability of it being in state 0. Then we take the inner product, right? So we take the inner product with this, bra, right? And then we have to square it, right? So let me call this ket as psi, right? Then I have to take 0 psi and then I square it. That's what we have seen, right? And so if you do that, you can see that you should get, the answer should be half, right? You should get 0.5. And as you can see here, you get 0.499 because of the way 1 over square root 2 is calculated, right? So here when we did the superposition, I already entered 1 over square root 2 because I wanted it to be normalized. But in general, we may not begin with a state that is normalized. So then how do we normalize if we have a state that is not normalized? You can use the Numpy normalization is Numpy. You can use Numpy to linear algebra and Numpy to normalize a state. So for example, we can create an unnormalized state 1, 2. So what would this mean? Right? For example, if I do 1, 2, right, this would mean that, for example, I would have some psi 1, right, plus 2 times psi 2. Right? This is clearly not okay, again, you're not able to, so something like that, right? So we are not able to, the total probability would be greater than 1. So it is clearly not normalized. So what you could do is you can take the unnormalized state. You can take the unnormalized state. So we define the unnormalized state as 1 and 2, like here. And then you can normalize it. That is, you can find out what is the norm. Norm is just basically you take, like if I have a state phi, right? The norm is going to be, I'm going to take phi times phi, right? Look at the inner product of it with itself. And then I can get the magnitude. If I want to get the magnitude, I can take the square root of that phi, okay, again, of square root of phi with phi. So that, if I divide with that, then I would get a normalized state. So if phi is an unnormalized state, if I take the norm and divide the phi with its a norm, then I would get a normalized state. So that's what we are doing here. So the way we take norm is we are taking with linear algebra norm of the unnormalized state, right? And then you can see that whatever you get is the normalized state, and then the norm of the normalized state is almost 1, right? Okay. So now the next thing we are going to do is, so we saw that whenever we write it as a column vector like 1, 0 or 0, 1, right? These themselves are meaningless because without the basis vectors, I do not know what these mean, right? So these are just components, right? These are just components. So these components do not have any meaning without the basis vectors. But I could change the basis vectors. For example, I could write I could just, if I have a two-dimensional vector, normal vector like I and j, right? Let us say I have some vector A, right, which is at 45 degrees, right? So then I can write this vector A as 1 over square root 2 I plus 1 over square root 2 j, right? Now, let us say I have a new coordinate system, right? Let's say I have a new coordinate system which is rotated by 45 degrees. So the new coordinate system is rotated by 45 degrees. So this is I prime. This is I prime, and this is j prime. So in the new coordinate system, A prime, right? Or A, sorry. In the new coordinate system, if I were to express the same A in the new coordinate system, then that would look like just basically simply I prime, right? So when I write A as 1 over square root 2 and 1 over square root 2, I have to specify what coordinate system it is. For example, if I do not specify the basis and I take this to be in, let's say, I prime and j prime coordinates, right? then that is a completely different vector from what I have drawn here, right? So the basis is important. And what we are going to look at is how we can change from one basis to another basis. So here we started with 0 and 1 as our basis. So let's say I can define a new basis called plus and minus, which is a linear combination of 0 and 1. So you can see here, this is called the Hadamard basis. And we're going to look at a Hadamard gate later on when we talk about quantum computing. So here we're creating a superposition of 0 and 1. This is positive, this is negative, right? Plus and minus. And so can you check whether these plus and minus, would they be orthonormal? What would be if I did this plus times minus, right? What would the value be? You can put that in the chat. What would this be? Plus minus for the Hadamard basis state. Would that be 0 or would that be 1? Okay, I see only one answer. Is everyone following? Okay. Plus times minus 1, Mahesh. Would that be 1 or 0? So please make sure that it should be 0, right? Because it is orthonormal, right? And so if we want to check that out, we can quickly check that out after we define the state. So we can first define the states very quickly, right? So we define state plus as 1 over square root 2, state 0, state 1, right? And then state 0, state minus 1, right? So we got this. And then, we could do, so very quickly, we could do something like, let's see, right? What we could do is, let's say, result is equal to np dot v dot of state plus and state minus, right? And then I want to print the result, right? So let's see, right? As we have seen, that gives us 0, right? So here again, we're doing v dot again because, so even if you did dot here, it wouldn't matter because both numbers are real. Oh, something happened. That should have, okay, I'm not taking the transpose. That's fine. So we'll continue to use v dot. So let's just continue to use v dot. So you get the result to be 0, right? So then what we have to do here is we want to express the other way around. We want to express 0 and 1 in terms of plus and minus, right? So then we could do that by changing the basis, right? By projecting onto these states, right? So what we are doing is we have expressed plus as 1 over square root 2, 0 plus 1 over square root 2, 1, right? So then if I want to express state 0 in these, if I want to express state 0 and state 1 in this new basis, right? So then what I could do is state 0 would be some number, some a times plus, right? Plus some b times minus. Our goal is to determine what is a and what is b, right? So as you can clearly see, then this a should be equal to, if I did 0, take the bra 0 and do the operation, then what I would get is simply, right, a would be equal to, or rather I could do, let me get the eraser, sorry, plus, not 0. So if I did with plus and I did from here, then I would get this to be, a would be plus times 0, right? Are you able to see that? And b would be minus times 0, right? So we just need to take the dot product of the state plus with state 0 for getting the first part. And then for getting the second coefficient, we need to take the dot product of minus with state 0. And that's what we are doing, right? So we take NPV dot of state plus with state 0, state minus with state 0, and then that's how we get the new state. And then we can express that state in the Hadamard basis. So you can see that, right? I hope you are able to follow. Let's see. Is there a question? They are matrices. Okay. So okay. And then so here the problem is that you have this doesn't look very good to see. So you can also use like this IPython. You can display math using LaTeX. So you can make it display like this. That's up to you. It's optional. When we use Qiskit, we have a much easier way to represent that this math. So basically, this simply represents in a better way, right? So you just see it in a better way. So here, this is an exercise for you where you express one in Hadamard basis and display it in LaTeX. I'm not going to go through this, but when the code is shared with you, you could go through the code yourself and make sure that you're able to follow through with this. Okay, so now we're getting to quantum matrices, quantum operations. As we saw in the last lecture, we can express quantum operations as matrices. So these quantum operations or quantum gates, which we are going to look at in the later half of this course, are going to be represented as matrices. So we'll begin with something called the Pauli X gate. The Pauli X gate is also called the quantum NOT gate. It is defined by this matrix. So what the NOT gate does is it flips 0 to 1 and 1 to 0, right? So what we want to do is first we want to define the Pauli X gate, and then we want to apply the Pauli X gate to a qubit that is in a superposition state, that is 0 and 1, right? So the way you can define a matrix is you can use an array, right? So the first row is 0, 1, and the second row is 1, 0, right? And then when you want to apply this thing to the state 0, so you can multiply a matrix multiplication, which we will see in a minute, or you can just do the dot product. Either way, it is fine, right? And then we can look at what comes out, right? So when I apply the Pauli matrix gate, state 0 is 1, 0. But after applying Pauli X, then the state flips. I get 0, 1. So that's why it's the NOT gate, right? 1, 0 becomes 0, 1. Similarly, state 1, which is 0, 1, when Pauli X is applied to 1, you get 1, 0. It flips, right? And if I pick superposition, right? So the Pauli gate flips, it's a NOT gate, right? If I pick the superposition, what would I get? Did you follow my question? If I pick a superposition, so if I have the Pauli X gate, which I'm going to write as sigma x. So sigma x acting on 0 gives you 1, and sigma x acting on 1 gives you 0. So my question is, what would happen if I applied sigma x on 1 over square root 2, 0 plus 1, the superposition state? Would it flip it? Okay. We have, right. So we have only one answer there, but I hope everybody understood it and everybody is listening. So we get the same state back, right? Because 0 is flipped to 1 and 1 is flipped to 0, right? That is only because these are equally distributed, right? If they are not equally distributed, then you get a different state. For example, like let's say you had in general alpha times 0 plus beta times 1, right? Then if I applied this Pauli gate on that, then I would get alpha times 1 and beta times 0, right? Which is not the same as the original state. It would be the same as the original state only for a special case when alpha is equal to beta, right? I hope you're able to see that. So that's what we did here. So when you apply the Pauli X gate, we got before and after, it looks the same. So then the exercise for you to do is we're going to look at some another gate called Hadamard gate. And so homework for you is to apply the Hadamard gate to state 0. So Hadamard gate is represented by a matrix like this. So whenever you're doing this exercise, what I would recommend is do it by hand first. see what you're going to get, and then try to write the code yourself. So for those of you who know, who are familiar with NumPy and who are familiar with Python, you can try to write the code yourself. For those who are not familiar, please look at the code and try to learn how to do this, right? So the Hadamard gate is basically what it does is it takes the state 0 and puts it into a superposition, right? So let's see here. So the Hadamard gate is given by 1 over square root 2, 1, 1, 1 minus 1. So if I apply this Hadamard gate H on state 0, which is 1, 0, then what do I get? Right? I get 1 over square root 2, right? This one goes here, this one goes here. So I get simply 1, right? And then this one goes here, this goes to 0. So I get 1. So this would give me 1 over square root 2, 0 plus 1. So I get a superposition state. So Hadamard gate, let's say I don't want to use H because I don't want you to think it is the Hamiltonian. So let's use sigma. So this Hadamard gate acting on 0 will give you a superposition state. Are you able to follow me? And we'll look at this Hadamard gate later on again. So here, you can check that out, and you see that when we apply Hadamard gate to 0, we would get this. So what would happen if we applied Hadamard gate to state 1? Would we still get a superposition? Right? So we can quickly check, right? We can quickly check what happens. I can change that to state 1, right? And so you get the negative state, right? You see that you got this negative number here for state 1, right? Instead of state 0, right? So again, you can play around with the code when Dr. Gargi sends you an email, and please make a copy for yourself, and you can play around with the code. So there are 2 exercises here. Again, please try to do them by hand without looking at the code. And then there's a question, I think. No, okay. So the minus sign. So the exercises are, you can apply a poly Z gate. Poly Z gate is given as 1, 0, 0, minus 1. That is defined here. So that's the poly Z gate, 1, 0, 0, minus 1. And then you have calculate the inner product of superposition with one state. So try to write the code by yourself. So I have some exercises here, and then you could look at that. So the next thing that I want to do, which is very important, is matrix exponentiation in time evolution. So we looked at this unitary operator, right? So when we looked at h psi, right, we looked at h psi, right? And then when h is time independent, we saw that if I am given psi at some time t is equal to 0, and I want to find psi at some time t is equal to t, right, at a later time, right, then what I could do is I could use a unitary operator that is like this, unitary time evolution operator, like u of t, right? So I could do u of t acting on psi of t equal to 0, right, would give me psi of t, right? And this unitary operator we define as the exponential, right? Exponential of minus iht by h bar. Here we're just setting t0 equal to 0, right? So here the Hamiltonian or any operator is a matrix. So here you are taking exponential of a matrix, right? So in general, the way we take exponents is if I just have something like e to the power x, it's a series, right? So e to the power x would be a series like this, right? So it would be e to the power x would be a series like 1 plus x squared by 2 factorial plus x cubed by 3 factorial, so on and so forth, right? So in a similar fashion, for the matrix, we begin with identity matrix plus a squared by 2 factorial, a cubed by 3 factorial, so on and so forth, right? So in Python, we can use another thing called SciPy, which is like NumPy, and we can do the exponential of matrix, which is called EXPM, right? And that is important for doing the unitary operators, for example, for time evolution, right? So here the example that we have is calculate the time evolution operator for a one single qubit Hamiltonian, right? So we consider a simple Hamiltonian like the poly X matrix, right? So the Hamiltonian is given by h bar omega times poly X. So our poly X is sigma X, which we have seen up here, right? So right here. So we have seen it acts like the NOT gate. So you should also be familiar with how to build the matrix if I am giving you these relationships. If I give you these relationships, how do I build the matrix for sigma X, right? So there would be 4 elements, right? So this element would be like a 0 times sigma X, right? Times times 0, right? And this would be 0 sigma X 1, right? And this would be 1 sigma X 0, right? And this would be 1 sigma X 1, right? So that's how we would build the sigma X matrix using the matrix element. So we already defined this matrix before, so I don't have to redefine it. So we have this poly X matrix. And then we are going to just take some random time, some pi by 2 time. And then we want to do minus IHT and take the exponential. So we want to take exponential of that argument. So that gives us the unitary operator. So this, when you do this exponential, it is doing that, it is expanding the series, right? That you have here, right? And so then I can take state 0, which is 1, 0, and evolve the state up to a time state t, right? So we can run that. So our Hamiltonian is 0, 1, 1, 0, right? And I'm looking at some random time 1.57 seconds, right? And then so the argument for minus IHT is basically e to the power minus I times h, right? We are getting, this is an exponential of a matrix. That's what we are doing, right? So we get the time evolution operator to be this, and then from time evolved state, right, after time t, we get something like this, right? So we get 0 and so some minus 1j, right? Here j is representing a complex number. It is square root of minus 1, right? So that's how we do the exponents. And then you can also look at eigenvalues and eigenvectors because these correspond to the observables as we discussed in the last lecture, right? So we have a matrix A, then the eigenvector is basically when you operate this A on the ket V, you get the ket V multiplied by this lambda, right? So these eigenvalues we can get using NumPy, the function called EIG that gives you eigenvalues and eigenvectors. So for example, if I take the poly Z matrix, right, which is very simple, right? Poly Z matrix is 1, 1, 0, 0, minus 1 like this. And so when you have a diagonal matrix like that, whatever is along the diagonal, they are the eigenvalues, right? So you can clearly see that the poly Z, the eigenvalue should be 1 and minus 1, like spin up and spin down, which we will discuss when we discuss the Stern-Gerlach. And so you can compute these eigenvalues and eigenvectors. That would be the output of the function EIG. And so we can run that, and we can also verify whatever. So you get the eigenvalues to be 1 and minus 1. And the outputs are 1, 0, which is the 0 vector, 0, 1, which is the 1 vector. Those would be the eigenvalues, right? Okay, and so the next question, this is an exercise, is you can do the time evolution with poly Y operator instead of poly X operator. So try to go through this by yourself and see whether you're able to do these and understand how to use these different functions in NumPy. So that's rather a very quick introduction to various things that we are going to use in this course as we go along for quantum computation. So I'll pause here and see if any of you have questions. Are there any questions? Please either put them in the chat or you can unmute yourself and ask. Okay. No questions. If there are no questions, then we will start with Qiskit. So Qiskit is a package just like the Numpy, right? And so let's go back to Chrome. Okay, so you have both of these links up there. So in Google Colab, if you want to do this on your local machine, you can download the notebook as either a notebook or a Python file, however you want, and you can run it on your local machine. So you can install Qiskit. If you're running it in Google Colab, right, you have to install Qiskit, right, and just make sure that you install the right version. If you don't install the right version, there is slight change in the way you call some functions. So, it would show something like that, right? And it would, so we are using, I think, 2.2.1. Yeah, 2.2.1. So if you're using older version, or the newer version, whatever, then some commands may look a little bit different, right? So now I'm just going to start with defining kets 0 and 1, like how we use NumPy. So we import NumPy as NP and define these kets 0 and 1, right? So this ket 0 and 1 is just like how we defined 1, 0 and 0, 1 column vectors. And then if you can do the addition, multiplication, all those sorts of things. And then we are defining M1 and M2, some matrices, just to show you how you define matrices. And then you can do the matrix multiplication. So now you can use this matrix multiplication. So when you do the matrix multiplication, it will tell you if the order is not correct. So this M1 is like an operator, right? It's a 2 by 2 matrix, and this ket is a 2 by 1 matrix, right? And what we will get is a 2 by 1 ket as a result. So when I do M1 with ket 1, I would get some result, right? And M1 with M2, I get a 2 by 2 times 2 by 2 matrix, I get 2 by 2, right? Simple matrix multiplication. So here the problem is, the way it appears. So you can again use LaTeX for better visualization. So for better visualization, you can go to Qiskit. Qiskit is the quantum module, right? And import from Qiskit.visualization this thing called array to LaTeX. So whatever is computed here, it would, like for example, when we did this np dot matrix multiplication M1 ket 1, it shows like this, sort of a little bit ugly to look at. So when you put it in LaTeX, it looks a little bit better. You can more clearly see like how you would write it. So you see, so you can do array to LaTeX. This is just for visualization. It just appears better, 1, 0, 1, 1. And you can also do fractions, right? Because now when you have fractions like 0.75 or 0.25, now it would show that as 3/4 and 1/4, right? So this array to LaTeX from Qiskit is a nice way to look at it. Okay, now in Qiskit, we can define the state vector. You have seen in NumPy how we define the state vector. We directly defined it as 1, 0 or 0, 1, but we can define the state vector by using the components. So here in Qiskit, when I define u as a state vector, it is automatically taking the basis. The basis is 0, 1 basis. So 0 would be a column matrix of 1, 0, and 1 would be a column matrix of 0, 1, right? So I'm just defining three different state vectors here. Again, Remember what a state vector means. This is talking about, it is encoding information about our preparation procedure, right? So I'm defining just simply 3 different states, right? And then what I want to do is I want to show you how we can display them in different ways. You can display the text. The text would display like this, or you can display it in LaTeX, or you can actually get the LaTeX source, because if you're writing papers, we usually use something called overleaf. So I can just copy this and paste it into overleaf, and it would show up something like this. So you can get the LaTeX source. But most of the time, I like to use the u.draw LaTeX because then it shows nicely like this how we write. Square root of 2 over 2 is same as 1 over square root 2, right? You can see that. And we looked at normalization in NumPy. In Qiskit, there is a simpler way of looking at normalization. That is, we can ask whether this is a valid state vector, because we have explicitly defined what a state vector is. If it's a valid state vector, then it must have a probability of 1, the total probability of 1, right? So if you look at something like this vector v, so let's see what is vector v. So let me copy this. Let me copy this part, and I want to draw v, right? So okay, so this is v vector. I hope you're able to see. Do you think v vector is normalized? Please use the chat to respond. Is the v vector normalized? Is it a valid vector? What do you think? Okay, we are seeing that people are saying yes. Please recheck. How do you check whether it's a valid vector, right? Is the norm 1, or is it greater than 1? What do you think? So let's look at that here. So what we have is vector v ket is given to be whatever 1 by 3 plus 2i by 3 0 minus 2 by 3 1, right? So if it is a normalized and valid vector, then what should be v by v? What should be the value of this? Please use chat to reply. Yeah, it should be 1, right? Dr. Dagi makes a very important point. We see that there are only 50% students interacting, right? So we seem to be in some superposition state with some students interacting and some students not interacting. So, oh, wow, we're able to directly write on that, right? Minus 5 by 9. Okay. Where did you get 5 from? Okay. Okay. Priyanshu, I think, yeah, thank you. So, yeah, so when you do the norm, you can see like even if you did this, right? So you get 4 by 3, right? Which would be greater than 1, right? You can check that out. So it is not a valid state vector. So previously, most of you have answered yes to see whether it's a valid state vector, right? So so you should get 4 by 9, right? So Let's see if it is a valid state vector or not. Oh, it is a valid state vector. Sorry, that's right. I think I entered you get 9 by 9. That's right. So you were right.
Ram, I think we can square both terms and then submit and see if it equals to 1. Like some math to do.
Saptagiri, I cannot hear your voice clearly. You said something.
I think we need to square both the terms and then submit. We should get
Yes,
1.
yes, it
Yeah,
is.
yeah.
I entered the wrong vector.
Yeah,
The one that I did
okay.
not. When I wrote the code, I intentionally put W as the unnormalized vector, but I forgot and I thought it is V. So
Okay.
so sorry about that. That's my bad. You guys did it right. So that's great.
That's it.
That means you guys are understanding. That's awesome. Right. So this one, when I draw W, this state, right? So this is W, right? This should not be normalized. So let's see W we have is 1, 3, 0 plus 2 by 3, 1, right? So if I did W times W, right, then I would get 1 over 9, right, plus 4 over 9, right? Then this would not be equal to 1, right? Are you able to see that? Right. So then this is not normalized. So the way we can checking normalization is you can simply ask. So we define this UVW in Qiskit as a state vector, right? So you can directly ask if that state vector is valid in Qiskit. So here we have defined the state vector UVW. So I can ask display whether it is valid. And so if it is valid, it would say it is true. If it's invalid, it is false. Sorry, I made a mistake with V. It was supposed to be W. So display with W dot is valid. You would get basically false, right? So you can also check with V. It should say that it is a valid state vector. So whenever you define a state vector, whenever you have a state vector in Qiskit, the first thing would be to check whether it is a valid state vector or not. And then if it is not valid, then you can normalize it to make it valid, right? So so that based on like whatever you want, like for example, you could change these numbers to make sure that it sums up to 1. Now comes the interesting part, right? Of measurements. So we can do the measurements. So I define this V as a state vector. So I can use this V dot measure, right? And it gives me the outcome and the state. So when I say outcome, that is when I measure, it tells me what kind of a particle it is, right? So for example, if it is in psi1 or psi2, if it is in state 1, 0 or 0, 1. And then it gives me the state that is post measurement, right? So let's see what happens, right? So I prepare the state V, right? Remember that when I define the state V here, that as the state vector, that is a preparation procedure, right? So now when I make a measurement, right, I'm making a measurement on that, right? So I get measurement is 1, and post measurement, now the state has changed because you measured it. Now your preparation procedure is the definition of V plus the measurement. I hope you are able to follow me. So your state is no more V, right? Because we define V as this, V as this. But after I made a measurement, then previously, I think Subhanshu said this is collapsing to -1 state. So it is not really collapsing to -1. The preparation has changed. So I prepared in this state, I defined it as this state, and then I made a measurement. So now my preparation is this state plus measurement. So then I get, I get some result for whatever measurement, and then my state has changed because my preparation is now different. Now, if I run it another time, what will happen? Will I get the same result? What do you think? Please answer in the chat. If I run this again, I ran it once, I got -1. If I run it again, will we get the same thing? Okay, so let's check that out. No, we did not, right? We got a different measurement, right? That is because now again, our post measurement, now our preparation has changed. So when I talk about when I talk about the V, right? So initially I have defined it some state preparation, right? When I make a measurement, right? First measurement, when I make a first measurement, I get some result. For the second measurement, the preparation is V plus first measurement, right? So it's no more V. The state is different, right? Again, for the third measurement, again, it is different, right? And then you can keep checking whether the post measurement state is valid or not, right? So the post measurement state is given by the state, right? So the variable state. So we can ask whether that is valid. So we can just simply copy that here. What do you think? Would it be valid or would it not be valid? So display, I hope this works, state is valid. True, it is valid, right? So let's run this again, right? It should always be valid. So if you begin with a normalized state, it should continue to be valid, right? So we will look at more of this kind of things in second part of the course, where we are going to use different gates and do this. So here, whatever we are doing, this is just fake quantum computing, in the sense that we are just simulating a quantum computer on a classical computer, meaning that I am explicitly doing linear algebra essentially. I am not doing any, this is like not being run on a quantum computer. I'm still running this on a classical computer, right? So, but in Qiskit, you can get tokens from IBM quantum computers, and you can actually run your code on an actual quantum computer, right? Which we will see later on. But for now, we are just sort of doing the simulated quantum computer, if you will, right? So now, when we actually want to take the measurement, then what we need to do is we need to measure multiple times. Remember when we did the Hitachi experiment, right? Then we were trying to do multiple times, right? So for example, let's say I have this state V, right? That is defined to be whatever state. Where was that? This state, right? So I want to make multiple measurements, or maybe we can take a simpler state. So let's take state U, which is 1 over square root to 0 plus 1 over square root to 1. So I'm going to take state U. So state U is 1 over square root to 0 plus 1. So what I want you to think about when you write something like this, I don't want you to think about this as a state that is associated with a single particle. I'm sorry if I sound very repetitive with this, but we are going to face a lot of problems. Even I face a lot of problems, because we are, every time we do the first course in quantum mechanics, we are thank you, Mahesh. Yes, that's right. It's a preparation, right? So it is encoding information, right? We are often taught with Copenhagen interpretation. So we say that when we make a measurement, it collapses. So really, that's not what is happening, right? So if I really want to measure this state, every time I make a measurement, I get some number, right? And that is only going to tell me about one single particle, like a localized hit of an electron. If I really want to see this state, what this state is, I have to make measurements. Let's say you don't know this, right? I did not give you this. I just gave you state U. You don't know what it is. It is a black box, right? It is some way of preparing the particle, right? And I asked you to determine the state. Then what would you do? You would keep making measurements. You would make one measurement. So you would make multiple copies of this, right? We make multiple copies, identically prepared systems, right? And we make measurements, right? So measure U, right? Measure number 1, right? Measure number 2, number 3, make multiple measurements like that. And then we take the statistics. And from the statistics, we can back calculate, see what is contained in the state preparation procedure, right? So here I sort of defined it already as this superposition, right? But, kind of forget that we defined it as a superposition. Just think that we define some vector u, right? And we want to look into what that state is. Then what we could do is we want to do multiple measurements. So I want to do statistics, right? So, and then plot it as a histogram. So you can, from Qiskit visualization, you can import histogram, and we can do the statistics. This number is telling you how many copies you are making. So when I say 1,000, I'm making 1,000 copies of this state vector. Again, when I'm saying copies, these are identically prepared systems. So we are taking 1,000 identically prepared particles and making measurements. And each time we make a measurement, we will find that the particle is in state 0 or state 1. And then after 1,000 times, we will arrange them into statistics and plot this histogram, right? So then you see that you have 538 and 462, right? You see roughly half. If you increase the number of measurements, let's say 10,000 measurements, then you see that probably, oh, we are doing with U. Let's do U, right? You see they're almost like 49 and 50, right? So as you increase the number of measurement, it will become more or less equal, right? So more or less equal now, right? So you then after you have made so many measurements, right? Okay, I hope it doesn't get stuck. Let's see. After you have made so many measurements, then you can say, oh, there is equal probability of it being in 0 or 1. So then my state preparation procedure must be this kind of a superposition. Are you with me? Are you able to see how this is when we define the state vector u or v or w, you can look at the state vector only after measuring multiple times, right? Any questions? Okay. So then let's go to some quantum circuits, right? So we define some quantum circuits like poly Y gate, poly X gate, so on and so forth, right? So here I'm just simply defining these operators. These operators are matrices, just like how we defined in Numpy. Okay, there are any limit of measurements. So Vedri, the limit of measurements here, we are running on a classical computer. So it just depends upon your processor and whatever you have. So, but usually law of large numbers, right? After 10,000, 20,000 trials, it's not really, it's going to saturate, right? So it's not going to give you any extra benefit. So I would say like if you do like 10,000 times, that should be good enough. But again, even 1,000 times may be enough based on what you are computing. But you want the measurement number to be definitely be large, like say like 1,000, 5,000, 10,000, so that you get an ensemble of measurements. Yes, these are single shot measurements. That's right, Saptagiri. These are you're doing multiple shots, and each of this is doing a single shot measurement. So here we are defining Y HST. This is the Hadamard gate, and this S is another operator. This T is another operator. So these are the T operator, right? There is a question that is, if you have states like 1 over square root 2, 0 plus 1, right, versus 1 over square root 2, 0 minus 1, how would you distinguish between these? Because when you make the measurements, right, you will end up getting the same states, right? So for example, we can check that out, right? So we can write that. We can go back up here and define another state vector. Command V. Let's call this U1 and let's make this minus, right? So I run this, right? So if I were to now do this histogram measurements with U1, which is this state. So this is U and this is U1, right? Then what would I get? Would I still get the same histogram? Yes, you get a similar histogram, right? Because when you take the probability, you cannot distinguish between this plus and minus. But the way you can distinguish that is that's why we have the quantum circuits, right? So when you have the quantum circuits, the superpositions would, the plus and minus states would be changed differently based on what operator you are using. For example, here what we have is a poly Y gate, the Hadamard operator, and so on and so forth, right? So for example, here I have one operator. So when you operate these things, then your state will change. So you can also do multiple measurements after you get one result from, let's say you take the qubit and you apply the Hadamard gate, and then you make the measurement again, right? Then you can distinguish between the plus and minus states. We will see that again in the future, right? So basically that is done using this command called evolve. So when we say evolve, it is going to basically evolve with h. So when I say v dot evolve h, what it is giving you is h times v. When you evolve with t, it is giving you t times v, right? So now let's say we made v is equal to v dot evolve h, right? So that means now, first we started with v. After we evolve with h, it becomes h times v. So now our state is not v anymore. Our state is hv, a new preparation procedure, right? Then I'm applying t, right? So then I would have THV. This is the new state, right? Then I am applying Y. Then I am applying S, right? So that's how you would get different gate. So you can use this evolve. Okay, name H is not defined. Okay, I did not run this, so let's run that. Okay, so we got those operators. So then we can. So when you do the multiplication evolution, then you get these, and then we can also we can draw that quantum circuit. So the way we were applying is we were applying H gate first, T gate first, H gate again, S gate again, and Y gate again. So that we can visualize in the quantum circuit. So there is a command for quantum circuit. So there is a question here. Phase sign. Okay. So okay, I think that was related to the previous discussion on plus and minus. So the quantum circuit, we can visualize the quantum circuit with HT, HSY, right? So we are multiplying, like we are doing H, operating H on V, then T on V, then again this, then again this. And then so you can just use circuit.draw to draw the circuits, and then evolve, and again find the statistics later on, like how you do these things. I think we are towards the end, so I don't want to go through the rest of the Qiskit parts, but you can go through this, and maybe tomorrow when we start the first lecture, we will go through a little more of this Qiskit and start our discussion on no cloning theorem, and more about state preparation and state determination. So this is meant to just introduce everybody to Numpy and Qiskit. We have not started discussing the quantum circuits and quantum algorithms, but this is where we are going to be in the next week. So this is just the introduction to get you used to that. So you should get the PowerPoints from Dr. Gagi, and then that should have links to these two Numpy file and Qiskit file. So please use that and go through the homework problems and the exercise problems so that you are able to follow. I know that some of you mentioned that you are already familiar with Numpy and Python. So maybe you want to, and some of you may even be familiar with Qiskit. Then basically, go through this, those of you who are not familiar, and then we will come back here tomorrow, do a little bit of this, and then move on to the decoding more about measurement, and talk about state preparation, no cloning theorem, coherence, and Stern-Gerlach experiment, and other techniques to prepare states in tomorrow's lecture, and also introduce what is entanglement. And that's what we will do tomorrow. So for today, I will stop here. And if there are any questions, please feel free to unmute yourself and ask, or put them in the chat. But if you do not have any questions, I think we should be done for today. Any questions? Okay. Dr. Gargi emailed all the material to you. So please join on time tomorrow. Uh, uh, please join in within the first few minutes because the attendance will be closed. So please make sure that you are there to ensure that your name is entered. If you have any questions, I'll hang around to answer. But if there are no questions, you are welcome to leave. Okay, Anuradha, any recommendation for books? So there were two books that we mentioned, and they're also listed in the PowerPoint slides. Yesterday's PowerPoint slide lists Leslie Ballantyne, Quantum Mechanics, a Modern Development. For Qiskit, there is no book as such, but there may be like a lot of maybe there is an IBM on IBM webpage. Maybe there is like Qiskit introduction to Qiskit. I think somebody made like from that material as a Qiskit book. So if you just like look at Qiskit textbook, you should be able to find it. But yeah, okay. So Saptagiri says that yes, Qiskit textbook is there on IBM site. But also you could just use GPT to sort of understand Qiskit. So you can do that. And for quantum theory, books are by Sakurai, Ballantyne, and Shankar. Can we make a WhatsApp group for discussion? Excellent suggestion, Vedveer. I think that's a great idea, but I'm not sure how people feel about their privacy and if they want to share their numbers or not. I am not sure, but maybe we can send out a poll to people, or we could use Signal if people want privacy, or Discord or something like that. So we don't have to really share phone numbers. Yeah, so you can make a group for students for yourself is Dr. Gargi's suggestion. Okay, Anuradha, you search for some books on quantum computation and quantum information. Yes, we will, when we get to week 2, we will have, so every lecture, whatever textbooks we are using to draw the information from, they would be mentioned. There is a book by Nielsen and Chong that we will use for quantum computation. That's sort of a gold standard. Then there is one by John Preskill from Caltech. That's also a good book. And I think those two books we will use mainly for quantum computing and quantum information. In addition to other resources, there are multiple other resources like QBraid or IBM Quantum Learning Site. They mention, but they do not, they're more simplistic. They do not go into the details of quantum mechanics. So they are sort of shut up and calculate or shut up and code kind of platforms. But for Qiskit and for learning those kind of things, that should be okay. But they may not, they may use Copenhagen interpretation too much, confusing people. But okay, Joseph Gruscha. I do not know. Do you know Gargi? Computer science. I don't know. I have never read that book, but thanks for the suggestion. I will check that out. But mainly we'll be using Nielsen and Chong. Yeah, yeah. I think yes, that's the standard. But again, as you see, most of these books that are written, the problem with most of these books is they use this Copenhagen interpretation, which is not entirely appropriate, because it sort of becomes deterministic in a way, and it becomes a little bit confusing when you are trying to explain query complexity and quantum gates in Copenhagen interpretation, where states are collapsing. and it is sort of unphysical. So what we are trying to do is use statistical interpretation, or at least give you an idea of, the deeper meaning of what the physics is. The math part is the same. So the math part can be done very easily. It is the same postulates, the same things. But trying to give you a different view from ensemble or the statistical interpretation point of view, which I have not found in many places. Mostly people use Copenhagen interpretation. So irrespective of what book you're using, you want to bear in mind that there are different interpretations of quantum mechanics, and how to look at these different results, and to distinguish between single shot measurements and multi-shot statistics and things like that. Yeah. For new learners, is Copenhagen interpretation necessary? No, but people are often taught with Copenhagen interpretation, usually because, to be very honest, it is much easier to teach with the Copenhagen interpretation. You just can shut up and calculate. That is the ease that Copenhagen interpretation has. But okay. Okay, so yeah, as Dr. Gagi points out in her response, no, it is not necessary. But if you want to understand other people, then I think you can look up this Copenhagen interpretation as well. But I think Vedvi, your suggestion of a group, I think you were the one who suggested that, was very good. I would be more comfortable if you want me be involved. Then I would be more comfortable with either Discord or Signal, where I do not have to share my phone number. Maybe that may be better for everybody, because I wouldn't want people may be uncomfortable sharing phone numbers. So let's maybe we can you can take the initiative to okay, Dr. Gagi has already taken the initiative to send a Google form. So then we can collect that and do Discord. Yeah, I think Discord is better. Well, people are electing prime ministers from there. If you don't use Discord, you can create an account. It should be pretty straightforward and simple, Anuradha. So you won't have to, nobody can see your phone number, right? So then that is more safer, I feel, because all of us are strangers to each other, right? Okay. Okay, guys, are there any other questions?